guys remember where did we stop last time? What distribution? I believe we finished the binomial and we started geometric distribution.
No, we finished it, but not quite that.
We finished the Bernoulli?
Bernoulli's distribution.
All right, okay, sounds good. So before I start, you guys know that we all have midterm on Tuesday, right? Okay, all right, sounds good. The midterm is gonna stop at the end of this lecture, so nothing beyond this lecture. So you revise most of the stuff in the notes, make sure they understand the problems in the homeworks. So I believe if you did this, you will do a good job on the exam. Okay, nothing crazy. Okay, so I'm just gonna revise with you what we have done over the last week. So if you guys remember, I'm gonna put it very quick. If you guys remember, last time we did the log normal distribution. By the way, the normal and log normal distributions are one of the most important distributions that we are gonna build on them for the fragility analysis and all this work. Because they are like continuous random variable distributions and we use them a lot in our research. However, the discrete random variable distribution is also important. We use them in the research and we're gonna see how we are gonna use them. But I just wanna revise with you the normal and log normal. If you guys remember, we said that x is equal to e to the power y, that's a log normal. X is log normal. And if we take ln to both sides with this way, I'm converting this distribution from log normal distribution to a normal distribution. Ln ey equal to y, that's a normal distribution. At the bottom of the log normal distribution, like if I say in an example as we did last time, I give you mu and sigma, and I told you that a variable y, the wind speed or the spectral acceleration of the flood depth should follow a log normal distribution. That means you cannot use like x minus sigma over mu. That's not, you can use it. You only use this if it's normal distribution. Once I say it's log normal, so this is going to be converted to ln x minus lambda x over xc of x, where lambda x is the logarithmic mean and xcx is the logarithmic standard deviation. So this is normal and this is log normal. Okay, that's, I believe, the only difference. And we had like the distribution function of this as we put it last time, the fx of x is equal to 1 over x exceed root 2 by, and then we have a parentheses, negative 1 over 2, multiply, have exponential burst, negative 1 over 2, ln x minus lambda x over xcx all squared, and then I have the parentheses closed. And then if we want to get that's the PDF, if we want to get the CDF, it's going to be fx of x, and this is going to be the integration of this fx function. Let's say fx of x, and this is from, by the way, this is not from negative infinity, this is from 0 because there's no negative log normal, okay? So this is until the variable x that we are looking for. Like if we are saying that this is the distribution, so the distribution is usually something like this. And if you want to integrate from 0 until a variable x, so you want all this area, so we're integrating from 0 to x. That's what we did last time, and somehow we were able to like say that u is equal to ln x minus lambda x over the xcx. So that's our assumption from last time, and we did this assumption so that we can use these tables, because we have the integration of these tables. These tables are represented phi x, let's say, or phi u, or x, whatever, equal to the integration from 0 up to u, and here we're gonna have 1 over root 2 pi, and this is the exponential of negative 1 over 2 u squared du. Either this is u or x or y, whatever, this integration has a solution, has a numerical solution. This is the numerical solution of this integration. You can use it because this is not for normal distribution. This is a numerical solution for this integration. You can form it for normal and you can form it for low normal. That's when we try to make it like a low normal. However, we use it for normal distribution as well. Okay, so when we do it for a normal distribution, that's what we use, and when we do it for low normal, that's what we use. Like we say here that the phi of len x minus lambda x over the cx is going to be equal to the value that you get it from the table. But if it's a normal distribution, it's going to be the same thing. The phi of x minus sigma over this is mu over sigma. This is going to be equal to the value that we get it from the table. So if I give you an example and I told you it's a normal distribution, so you are going to make the phi of this value equal to the value of the table. If I give you an example and I told you it's a log normal, so you're going to get this value and get the rest, the value from the table. All right, so that's for the log normal distribution, and that's still, we are under the umbrella of continuous random variables. So last time we started discussing discrete random variables. So let's say that we have, start with Bernoulli. I'm gonna write it very quick. The Bernoulli distribution. Bernoulli distribution, as we said last time, do you guys remember what it is? What does it represent?
It's discrete distribution, two options.
Yeah, two options. What are they? Success or fail. It's either being a lawyer or not a lawyer, engineer or not an engineer, either head or tail. That's the output. It doesn't have to be the output 50-50. The head and tail is 50-50. But if I told you, like last time, if we had 1 out of 100 as an engineer or as a lawyer, that's not a 50-50, that's a 0.01 and 0.99, okay? So it has a function, it's kind of a silly function, but the probability of success is B, and the probability of fail is 1 minus B. So that's actually makes sense. So if we are saying X is either 0 or 1, 0 is fail, and 1 is success. Okay. So it's either 0 or 1. What we are looking for, as we said last time, that the probability of X, the probability of your random variable to be equal to X, which can be a success or fail, is always equal to the probability B to the power X multiplied by 1 minus B to the power 1 minus X. Whereas B is the probability of success, and 1 minus B is the probability of fail. So the first thing that you have to do in your problem is to determine what is the probability of success and what is the probability of fail. Like if I told you 5 out of everybody in the US is a teacher. So you find the probability of a teacher, like 5 out of 100, so the probability of being a teacher is 5%, not a teacher is 90. That's the very thing that you have to find out. So if you want to find, for example, the probability of X to be equal to 0, like you having a fail, so this is going to be to the power 0, so B to the power 0, and this is going to be 1 to the power 1 minus 0, so you will end up that this is equal to 1 minus b, right? That's the probability of fail. Same thing if you want to find the probability of success, this is going to be equal to b. All right, and we put here like the mean and the standard deviation of this. So the mu of the Bernoulli is b, and the sigma square of the Bernoulli is p multiplied by 1 minus b. That way we have done. Mu is the expected value, and here this is the variance. All right, and I put a proof here, how to prove it, and I put an example. So let's continue to the binomial distribution. So number 2, binomial distribution. So what about the binomial distribution? The binomial distribution is the distribution of x that represent the number of success in n trials. Like right now, let's say that we are rolling a dice. I'm saying, what is the probability that you are getting 6 on the dice 2 times in 5 trials? Like, let's say you throw it 1, 2, 3, and 4 and 5. What is the probability that you get 6 2 times? But let me put it in a very easy way. What is the probability of getting 6 1 time?
1 over 6.
1 over 6. The thing is, I want to find what is the probability of getting 1 6 in 2 times, or 1 6 in 3 times, or maybe 2 6 3 times. That's the binomial distribution. Okay. So, and I'm gonna give you an example how we handle this in natural hazard, because it's the same concept applied for natural hazard. What is the probability of getting a 100-year event in 5 years, or 200-year events in 6 years? Something like this. All right, so basically that's how we do it. We say that the probability of x equal to x, whereas x is the number of success in n trials, is equal to the combination of n and x multiplied by the probability of x, 1 minus b, n minus x. Okay, let's find out what are these. So x can be equal to 0, 1, 2, 3, up to n number. Like, you want to find the probability of getting a value in an n trials. Definitely x is less than the n trials. Okay, I want to find how many success, how many I'm getting 6 on a dice and 5 trials. Okay, you will never get 10 6 from like 1 trial. Yeah, I mean, that's how we do it. And this thing, the combination, if you guys remember, this is equal to c n x, which is equal to the factorial of n over the factorial of x multiplied by the factorial of n minus x. Do you guys remember this?
Yeah.
Have you seen it before? So this is when we want to choose, if you guys remember, it choose x success out of n trials. This is the combination that you guys maybe take in high school or something. I got it like in high school, and also in the first year of engineering. So basically, if you want to find the x success in an n trials, it's a combination, and you can find this online how to prove it. It has a proof. So basically, that's the factorial of n. And if you guys remember, the factorial of 5 is like 1 multiplied by 2 multiplied by 3 multiplied by 4 up to 5. So that's how you get the factorial. And then over the factorial of x multiplied by the factorial of n minus x. This is how you can get the combination of x success in an n trials. This is the probability of success to the power of x, and this is the probability of fail multiplied by the probability of n minus x. Okay, so the expected value of x, or the mean, is, or this is mu, is equal to n multiplied by b, and the variance sigma squared is equal to nb multiplied by 1 minus b. So that's the mu and sigma. And by the way, this is the probability of x equal to x. What is, if you want to find the probability of x less than or equal to x? So if you want to do this, you will have to do, like, do you guys remember when we have a discrete random variable? This is the BDF. And this is the CDF. If it's a continuous random variable, we do integration, right? But if it's a discrete random variable, we do the summation of the BDF. So we sum on the BDF from x equal to 0 up to the x of interest, and then I'm gonna do the whole thing again. So it's gonna be n x multiplied by b to the power x multiplied to 1 minus b and the minus x. That's how we do it. All right. So this means, what is the probability of getting 2 success, let's say 2, in the trials? So basically I put here 2, like let's say I have 2 and 5. I want to get 2, 6 from rolling a dice. So I have an example here. Okay, let's say I have a dice. A dice is rolled 5 times. What is the probability of 6 to show 3 times? Let's find out. First, when we're rolling the dice, what is the probability of success to get 6?
1 over 6.
It's equal 1 over 6. If I say, what is the probability of getting 6 and 3?
It would be 2
2 over 6, because it's 2 outcomes. So what is the probability of fail? 5 over 6. Okay? What is the number of x that we are looking for from this problem?
6.
3.
3, because, okay, I'm looking for the probability of 6 to show 3 times, so I have 3 success. What is the number of the number of experiments? 5, right? So I'm rolling the dice 5 times, and I'm looking for 3 success in these 5 times. Okay? So once you lay this out, you solved the whole problem. So basically, I substituted this probability. So what is the probability of x to be equal to 3? So here I'm gonna put n is equal to 5, and I'm looking for 3 success out of these 5. And I have the probability b is equal to 1 over 6 to the power x, which is 3, and 5 over 6 to the power n minus x, 5 minus 3. And then I calculate. So this is gonna be equal to the factorial of 5 over the factorial of 3 multiplied by the factorial of 5 minus 3. And here I'm gonna have 1 over 6 to the power 3 and 5 over 6 to the power 2. And the solution is gonna be 0.032. That's the solution. Okay, did you guys got that distribution? All right. So basically, I would recommend, don't involve yourself in a lot of math, but if you want to be conservative where the these stuff got from. Maybe you go revise back on the math concepts behind this. Because I remember when I was taking this in math, I was like, oh, where's this came from? So there's like a proof behind it, and also there's a proof behind this, but it's very, very long story. So we only wanna use the equation itself. We don't wanna waste a lot of time knowing where this stuff came from right now. Okay, so let's get to the next distribution, the one after this one, which is the geometric distribution. All right. So the geometric distribution is the distribution of a number of trials needed to get a success in repeated Bernoulli trials. So it's still based on Bernoulli distribution. So basically here in this problem, I told you, what is the probability of 6 to show 3 times? So you are looking for 3 success. Geometric distribution is only interested in the verse success. What is the probability of getting your verse success? Like, let's say I did this trial 10 times. What is the probability of getting my verse success in all these trials? And that's actually the basic concept of the return period. Because when we say 100-year event, that means it's a one event, not multiple event. I didn't tell you what is the probability of getting 200-year events or 300-year events. Once I say that, that means I'm going to a binomial distribution. But if I'm looking at one event that has success, that's geometric distribution. And you have to be careful with this, because when I say it in the exam, I'm gonna give you the problem. I'm not gonna tell you if it's geometric or binomial. You have to figure it out yourself. Okay? So for this one, I didn't tell you, but you figured out because we are looking for a number of success in the trials. But when I tell you, what is the probability of getting the your reversed 6 in 10 trials for this problem? So that means that's a geometric distribution. So that's how I define it here. It's the distribution of the number of trials needed to get the success and repeated Bernoulli event. So in repeated Bernoulli event, let's say that you roll the dice. You got failed. You didn't got 6. And you rolled 1 time, you got failed. 3 times, you got failed. And you kept rolling until you got your success. So X is the success. X is the success trial that you got, and the one before it is the X minus 1. So here you had 1 trial, you didn't get it, the second one, the third one, until X minus 1, up to X, you got your success. And the probability of success in a geometric distribution is the same. Success is B, and the probability of fail is 1 minus B. Where X, let's say here, X is the number of trials needed to get the verse success. In and N trials. So X over there in the binomial distribution, it's the number of success that you get in the trials. But here is the number of trials you need to get the verse success. Okay. All right. So let's write the probability of X to be equal to X. So the probability of X to be equal to the number of trials needed to get your verse success is equal to 1 minus B to the power X minus 1 multiplied by B. and that's actually the FX. So we, like I read it one more time. That is the BDF. The CDF is the summation, right? Is the summation from x equal to 0 up to x multiplied by 1 minus b, x minus 1 multiplied by b. So that's actually the summation. But also, if you used the some algebraic equation and expand this binomial, it's gonna, you will find out that this is equal to 1 minus b, or multiply to the power x. That is the CDF. So you either use this equation or directly substitute in this one. That's the CDF. All right, and the expected value of x. Usually when we have a distribution, we're always interested in the BDF, the probability density function, and the CDF, the cumulative density function, and the mu, which is the expected value of x, and the sigma. That's what we need from distributions. So mu of this distribution is 1 over b. And sigma is equal to root 1 minus b over b. And by the way, the expected value of a geometric distribution is equal to the return period when we talk about natural hazard. So return period concept is a geometric distribution. Like if we say if I told you what is the probability of a 100-year event, 100-year event, 100 year is the return period. That's 100. So if you want to get the probability, like right now I told you a 100-year event, so 1 over b equal 100. If you want to get the probability of the 100, is 1 over 100, and this is equal to 0.01. That's where the concept, if I told you an earthquake has I have an earthquake has a return period of 1,000 years, so that means it's a geometric distribution. So if you want to find the probability, and the 1,000 year is the mean here. So the return period itself is the mean of the geometric distribution. If I told you a flood event is a 500-year flood event, that means the 500, that means that this is a geometric distribution and its mean is 500. And if you want to find the probability, so the probability equal 1 over the return period, and it's equal to 0.01. And if it's 100, if it's a 500 year, it's gonna be whatever 1 over 500. Okay? Does anybody have any questions so far?
May I ask a question?
Yeah, sure.
If you would like to calculate CDF for that question, should we get summation for all x? Like x is equal 1.
This one, yeah, you'll have to do this, like let's say,
5 to 1.
okay, let's say this question, a dice is rolled 5 times. So what is the probability of 6 to show 3 times? So you want to find out what is the probability of 6 to show less than 3 times. So you will have to do it first for 1. So you will put x here equal to 0, like not to show up. Less than 3 times, that means 0, 1, 2, and 3, less than or equal. Okay, so you'll have to do it for 0, and then you have to do it for 1, 2, and 3, and sum all of them. Okay,
Thank you.
all right. Okay, does anybody have any questions so far? Okay. And if I told you what is the probability of 6 to show more than 3 times, so you can get the probability to show less than 3 times and then take 1 minus. Okay. Let's get back to the wind example that we had from last time. guys remember, we had this example before. We have annual exotreme 3-second gust wind speed described by a log normal distribution with mu equal to 60 mile per hour and V, which is equal to sigma over mu equal to 0.2. That's the coefficient of variation. Last time I asked it for the requirement number 1. If you guys remember, what that was the requirement number 1. What is the design wind speed for a structure to be designed for a 50-year event? And I told you this is kind of like a combination between geometric and log normal distribution, since I told you event to happen in 50 years. So you need a success in 50 years. Okay, so I drew this last time. This is how the gust wind speed look like if we are looking for events. And here I have the V in mile per hour. So usually the wind is something, you have events like this, the wind like this. So that's each one of these peaks is the 3-second gust wind speed. So at some point you are going to have your 50 here. That's the event that you're looking at. That's the 50 year. But you have lots of other events until you get to your 50 year. So since I told you there's a return period, I told you what is the design wind speed for a structure to be designed for a 50-year event. So basically here, the probability of this event, that's the mean of a geometric distribution, and it's equal 50, as I said here. This mu is equal to the return period, so the mu is equal to 50, so 1 over the probability of this event is equal to 50. So if you want to find the probability of this event, so it's going to be 1 over 50. Okay, so this is equal to 0.02. So the probability of your 3-second gust wind speed to exceed 50 mile, the probability of the V50 to happen is 0.02, or the probability of your wind speed to exceed the V50 is 0.02, right? So that means I can write it that way. The probability of your wind speed, that's all events that has V. Let's say that the wind speed here is V1, V2, V3. All these wind speeds are like not the V50. If you guys remember, the result was 90 mile per hour last time. Let's say this wind is like 70, and this is like 65 and 67. You still didn't exceed the V50, okay? So the probability of your V to be more than the V50 is equal to 0.02. You have 2% chance that your wind speed to exceed the V50. And similarly, we can say that the probability of V to be less than V50 is 1 minus 0.02. That means it's 0.98. So that's where we got the 0.02 last time. That this is a geometric, once you hear a return period, so your mind go to the geometric distribution. That means the return period is the mean, and the mean equal to 1 over b, and the probability of this return period to happen is equal to 1 over the return period. So if I said a return period 100 year, so the probability of 100 year is 1 over 100, which is 0.01. I told here, like 50 year, so 1 over 50 is 0.02. So that's the first piece of the puzzle. I got the probability of v less than v50, but this is not what I'm asking for here. He's asking for what is the wind speed. He wants to find what is the v50 is. He doesn't want the probability of v to be less or more than v50. He's asking for the wind speed itself. Because I already given what is this probability is. It's already given. So that's why he give you this piece, that the wind speed in this problem follow a log normal distribution, so that you can say that you want to find the probability. So you can put this as a phi of ln v50 minus lambda v over the xcv is going to be equal to 0.98, right? Because that's the definition. So the probability of v is less than v50 is equal to the probability of here. So I have phi, and if you guys remember, I believe I put it here somewhere. This phi was representing the PDF, like let's say the phi of ln v50 minus lambda x over xcx. That was the fu, and that was the integration from 0 to u, 1 over root 2 pi exponential negative 1 over 2 u squared du. And we are looking from 0 to v50, or ln v50. Our, let's say, because this is not supposed to be like this, u is equal to, let's put here u, and u is equal to ln v50 minus lambda x over the xc of x. That's how it is. All right? You guys got that? All right, so this is basically my u, which is ln v50 minus lambda x over cx. So right now I want to find lambda x, and this is going to be equal to ln mu over 1 plus v squared under the square root. And when you calculate this, given that I already gave you the mu, it is 60, 1 plus 0.2 squared, so you'll find out that lambda x is equal to 4.07, and the cx is equal to root ln 1 plus v squared, and this is going to be equal to ln 1 plus 0.2 squared, and this is going to be equal to 1.0198. So phi of ln v50 minus 4.07 over 0.198 is going to be equal to 0.98. And how I did it last time, I take phi inverse and I said ln v50 minus 4.07 over 0.198 is going to be equal to the phi inverse of 0.98. Basically, I take the phi inverse for both sides. If I take phi inverse of both sides, this phi is going to be gone, and I end up with phi inverse of this side. So last time I told you that we have to go in the tables, and you go with 0.98 in the table, try to find the value of 0.98 and get the value of this. And if I go with 0.98, looking at the tables, it's gonna be equal to 2.06. So once you find this, basically you can multiply the 2.96 by 0.198 and send the 4.7 the other side and take E to both sides, and V50 is gonna be equal to 87.24 mile per hour. That is the V50. That was the first piece of the problem, okay? So I try to explain it more this time because we take the binomial, the geometric concept, so you guys can know where mu is coming from, how did I calculate its probability, because I didn't say it last time. So that's the first part of the problem. I didn't do any log normal distribution until this point. All this was geometric because I told you within there, once I found the probability, I use it in a log normal distribution. So let's find the second piece of this problem. Let's solve it. So requirement number 2, I'm asking you to find out what is the probability of that first such wind V50. What is the probability of this V50 occurs? What is the probability of such wind occurs within 5 years? All right, I want you to focus and tell me, based on this question, what kind of distribution should I use? Geometric, right?
Geometry.
Because I'm looking for the first success in 5 years. What is the probability of first such wind speed to occur within 5 years? Look at this, because this is very tricky. I told you within 5 years. It doesn't matter if it's the first year, the second year, the third year, fourth year, it doesn't matter. So so you will tell me, is that a PDF or a CDF?
CDN.
So if I told you what is the probability of the such first wind speed to happen in the 5th year only, that means it's a PDF. But within 5 years, that means what is the, so you will sum all the probabilities. It's probability to happen in the 1st year, 2nd year, 3rd year, 4th year, up to the 5th year. So you have to be very, very careful to the wordings that we have here. Okay, so how did I translated this problem? Since he is so versed, that means I knew that it's geometric. Sorry. Yeah, it's geometric. Metric distribution. And since I said within 5 years, I knew it is the probability of x less than or equal to x. But if I said the probability to happen in the 5th year, that means it is the probability, let's say, if I said this in the 5th year, like if it's the same problem and occurs, what is the probability of such wind speed occurs in the 5th year? This is gonna be, what is the probability of x equal to x? Do you guys understand that? Okay, so let's say that we translated the problem and we are gonna go with within the 5 year. So let's see if we have this rule here. Okay, if you guys remember, this is the PDF. You have 2 options. The first option is to use this. Like first, you find at x equals 0, you put here like 0. Just there's something here. This is Yeah, this is right, okay. Because I said there's no x equals 0. You have here, x is equal to 1. You have it here 1, 2, 3, and 5. Okay, so you either have this and write and get the probability, because I did it here, the probability of x less than 5, and I kept counting, like let's say, I said, what is the probability? That's what I'm looking for, the probability of ux to be less than 5. And what does that mean? What is the probability of the success to be less than 5, or happen in the first 5 years? So to do this, can you guys tell me what is written here? Like, I have 1, the summation from x equal to 1 up to x equal to 5 of
1 minus b.
1 minus b to the power
X minus 1.
x minus 1
Divided by
b, right?
Yes.
Okay, so if I want to find it for the first one, so I'm gonna be 1. First, what is the probability b?
Equal 1 to 02.
It's 1 over 50, which is equal to 0.02. That's the probability of success. What is 1 minus b? Is 0.98. So I have 0.98 multiplied by 1 minus 1 is going to be 0, multiplied by 0.02 plus 0.98 multiplied by to the power 1 multiplied by 0.02 plus 0.98 So this how I'm gonna put it that way. If you calculated this with your calculator, this is gonna give you 0.096. That's a one way to do it. There's another way to do it is you use this closed form. 1, this is equal to also 1. Can you guys tell me what I have here? 1 minus
1 minus b to the power x.
the power x. So if I did it, that's an easy way. 1 minus 1.02 to the power x. So I have x here is equal to 5. And once you calculate this, it's going to give you also 0.096. Okay, so both ways, and I believe the closed form one is much easier, but you can calculate both, it's going to give you the same answer. All right, so that is the probability of having burst such wind speed occurs within 5 years. Does anybody have any questions so far? Is that concept difficult, easy, medium? Maybe it's kind of confusing sometimes, but if you focus, you will get it. And it's very important actually if you are gonna work in the risk and reliability field, or if you're gonna work with insurance companies, it's all about probability. Everything is probability. And the analytics there, they are really, really smart people. They have very, very good basics and reliability and probability. So you can't get in this industry without these bases. So you have to have a good firm on it. And definitely you will have to have a really good toolbox with you, like to be very good and do this analysis with MATLAB. And there's other tools, like there's R. There's a software called R that's mostly for statistics. So that's also a good tool. But we are not doing pure statistics. We do structure analysis, we do a lot of other stuff. So usually other softwares like maybe Python or MATLAB or something. Okay, so the ask number 3 in this problem, I'm asking you, what is the probability that you exactly have one exceedance of V50 in 5 years? All right, so you guys tell me what distribution I should use if I'm asking you that you are gonna get one exceedance in 50 years. What if I say 2 exceedance in 50 years? That means I'm meaning how many success you are gonna have in 5 years. So right now, I'm asking for 1 success. If I ask it for 2 success in 50 years, that means 2 out of 5. So that's what is the name of this distribution? Binomial distribution. Bernoulli is the success or fail. So we don't have success or fail. And yeah. All right, so let's write this. So that means, okay, first I have to put B. What is the value of B? B is 0.02, right? And 1 minus B is 0.98. And X is equal to, and N is equal to. So N is equal to 5, and X is equal to 1. I'm looking for 1 exceedance in 5 years. So if it's 2 exceedance in 5 years, so I'm looking for 2. All right, so here's the function. If you guys remember, the probability of X to be equal to X is gonna be equal to N(x) B to the power X and 1 minus B to the power N minus X. Okay, so let's put it here. I have 5, I have 1, I have 0.02 to the power 1 and 0.98 to the power 5 minus 1. So once you do this, let's put here, this is the factorial of 5 over the factorial of 1 multiplied by 5 minus 1 factorial. And this is going to be equal to 0.02 to the power 1, 0.98 to the power 4. So once you calculate this, you'll find that the value is equal to 0.0922. Yeah. Does anybody have any question on this part?
Professor, I have a question.
Yeah.
In the original example, if it was not mentioned that it's a log normal distribution, then what would we do?
Well-
It's not given that it's a log normal distribution.
Well, I have to, because if I didn't, you'll not be able to solve for the probability of V50. Yeah. But I can't, like, let's say that we excluded the first part of this problem, like I didn't tell you what is the mean and standard deviation, I can still proceed with this because I already give you the return rate. So this part, these two values is needed to get what is the value of V50. I don't know where did I get it, but I believe maybe it was somewhere,
The right side.
somewhere here.
There.
Oh, it's here? Oh, okay. Yeah. Why did I have binomial distribution? Oh, okay. Yeah, so, so here to get the V50, but here I didn't use the V50 anywhere, I just wanna use the probability of the V50. So if I only wanna test you in discrete random variables and like that you understand the geometric, binomial, and Bernoulli, I wouldn't ask you for this part, like the first one. I would just like tell you animals 3-second gas wind speed is described whatever, and maybe I wouldn't tell you. I would just ask you what is the design wind speed for a structure to be designed for a 50-year event. I'm not gonna ask this, but what I'm gonna ask you, I can ask this question right away. What is the probability of burst of V50 to happen within 5 years? Just this question. Like here, like I have already an example, so let's. Okay, like look at this example. What is Look at this question. I didn't give you any mu or any lambda. I just asked you directly, what is the probability of two 500-year flood events to happen in the next 40 years? No, I didn't give you any data. I didn't give you, because if I give you data, I would ask you, what is the value of flood? Because you have to know what is the mean of the flood depth and what is the standard deviation of the flood depth so that you can know what is the flood depth is. But if I didn't give you any information about mean or standard deviation, I wouldn't ask you about flood depths or wind speed. But here, it's all about probability. So right now, I'm asking you the probability of two, like that means that you are gonna have two success.
Out of 4.
And I give you the 500, why did I give you 500 year
That is
event?
the probability.
So that you can get the probability, right? So since it's a 500 year, that means it is a geometric distribution. So once I know this, I know that the 500 year is the mean, which is the return period of a geometric distribution is equal to mu, and this is equal to 1 over b, which is the 1 over the probability of success. So the probability of success is equal to 1 over 500. And this is equal to 1 over 500 is equal to 0.0025 or 0.5, I guess.
Two.
Yeah. 5 over 100. 0.002?
Yes.
All right, so if it's 1 over 1,000, it's gonna be 1.001. All right, so that's the first part of the problem. And then I told you what is the probability of 2 to happen in 40 years. So we are looking for x equal to 2 success out of n 40 years, right? So what is this distribution is? Binomial, right?
Binomial.
So that means binomial distribution. So I'm gonna solve it like this. Probability of x to be 2 is gonna be equal to, I'm looking for, I have 40 trials and I'm looking for 2 success out of these 40 trials, multiplied by the probability of success, which is this one, and the probability of fail is gonna be equal to 0.98.
Yes.
No, 998.
0.998.
Oh.
0.998.
0.998. Yeah. All right, so this is the probability of success to the power x multiplied by the probability of fail. It's going to be n minus x. So this is going to be equal to 40, the factorial of 40 over the factorial of 2, and here 40 minus 2 factorial, and the probability is going to be 0.002. X is 2, 1 minus 0.002, which we just calculated, is going to be 0.998, and this is going to be equal to 40 minus 2, which is going to be 38. And this is going to be equal to 0.0029, which is 0.3% chance. So there is a 0.3% chance of getting 5, and that's a general. That's a general, like that's a real. Like let's say we're talking 100-year event, and I can ask you, like in our world, in the risk analysis world or the insurance world, and we talk about 100-year events to happen in Miami-Dade County, like 100-year flooding or 100-year rainfall. You need a lot of information to know what is the probability of the whatever, like to get information about the event to be a 500-year. But let's say that we know it. We know that there's an event is a 100-year event, and that event is like when the flood depth is equal to 2 meters. That's a 100-year event. Okay? So if I tell you what is the probability of 2 or 300-year events to happen in the next 20 years or in the next 5 years? Okay? Definitely, let me ask you, what is the probability is much bigger? The probability of 100-year event to happen in the next 2 years or it happen in the next 50 years?
Next 50.
In the next 50 years, because there's much higher probability to happen. But in 2 years, that you can try yourself. Like try to put 2, like 2 event, like one, like put 1 and another one put 50. Okay. All right. Because once you put 50 here, this number is gonna get bigger, and yeah, it's gonna make a difference. And here, this number is gonna change, and this number is gonna change. So yeah, I mean, that's in general what we need, or what I want you to understand before we do any actual applications. So at this point, this is, I believe, the last thing I'm gonna talk about, theoretical and reliability. Moving forward after the midterm, we're gonna use all these concepts in applications, okay? So I want you, like, that's not too much, I believe that's about 2 lectures, right? So, by the way, the risk and reliability course is huge. Like, we could move forward with Poisson distribution, type 1 and type 2 distributions. And we could spend our whole semester talking about distributions and equations, and I hate to do this. I know it's important to build the good basics, but I also want you to practice, want you to do some application. So that's why I make the course stop at the mid semester, and that's what I do with most of my courses. I do half semester basics and half semesters application. So I'm gonna stop here at the point of, like, I want you to understand mostly the distribution. Right now you understand what is mean, what is the standard deviation, what is normal distribution, what is log normal distribution. So when I say this moving forward, you should have these basics. Moving forward in the next few lectures, next lecture we are gonna have a midterm. After the midterm, I'm gonna teach you, maybe if you want, like, I know that you are gonna be busy studying for the midterm, but I need you to build good basics in ArcGIS. And if you want to be familiar with the flood hazard, maybe you start watching videos about hydrologic and hydrodynamic modeling, because we are gonna have some flood application. I'm not asking you to be expert, just to understand the process. I'm gonna give you the information, like it's the same process for any hazard risk analysis. To do hazard risk analysis, you have to have a hazard map. Like, if you want to do hazard risk analysis for earthquake for Los Angeles, you have to have a hazard map for the complete Los Angeles, so that you can know what is the spectral acceleration at each building. If you want to do a hurricane or a wind risk assessment for Miami-Dade County, so you have to have a wind hazard map so that you can know what is the wind speed at each building. Same thing with flood. If you want to do flood risk analysis, you have to have a flood hazard map for the study area that you have. So it's all the same, but maybe you are going to focus on flood or wind applications, but it is the same for earthquake, same for tornadoes, same for any other hazards. It's just what is going to be different, the hazard maps and the vulnerability curve. It's going to be similar vulnerability curve, but for different hazards. Like our vulnerability, if we are talking about flood, on x-axis we have the flood depth, and y-axis the probability. If we talk wind speed on the x-axis, the probability of damage on the y-axis. If we talk earthquakes, spectral acceleration on the x-axis, and the probability of damage on the y-axis. That's the vulnerability. So I'm gonna start with you step by step. I'm gonna teach you how to use the ArcGIS, but I'm gonna give you just introduction. So you will have to work with yourself to try the software, to try new things on the software, maybe watching some YouTube videos, how to use the software, because it's very, very important if you are gonna get in our field that includes analysis at the community level. So I'm gonna teach you basics, how to use ArcGIS, how does the interface look like, what is the most important things that you need to get from the ArcGIS. ArcGIS is huge, it's really big, but we are gonna use just limited tools in ArcGIS. We need to know how to handle something called shape files of the community, how to do analysis, how to extract data, how to export data, how to import data, how to visualize data. I'm gonna teach you this, but for me, even myself, if I'm working with this software and I stuck with something or I wanna do something, I go on Google or YouTube, how to do this on ArcGIS. And then I'll find hundreds of videos to do it, okay? So that's the first tool that we need to learn. The second tool that I want you to get familiar with is MATLAB. You need to have the basics of solving equations or solving algorithms using MATLAB. At least you have the basics. I'm gonna teach you, but I'm not gonna teach you the basics, but I'm gonna teach you, showing you how I run my functions. You are gonna have the functions that I'm using. I'm not gonna give you the codes, but I'm gonna give you a video that show you the code step by step, so that you can maybe watch the video step by step with me and write the code while you are watching. And I'm explaining every piece in the code. Like every piece in the code, this part is doing this. If you don't understand how is the for loop in MATLAB getting written, maybe you go to YouTube and write how to run a for loop or how to write a for loop on MATLAB, or how to do this, okay? So that's how it's gonna work moving forward. We have a lot of work ahead of us. So maybe from now, I know we have around 10 students in the class. After the midterm, we are gonna have a project. So when I taught this class 2 years ago, everyone will find himself on the project. This year, I'm gonna make it like, because I saw some students' feedback on the survey, they say it was too much work. So I'm gonna make 2 students on the project. So we are gonna be 2, every project only 2 on the project. So you basically try to work together, and I think the best way that you both learn much is that you both like learning how to write the coding. So maybe divide the work by both of you write different pieces of the code and try somehow to integrate it together. Whatever is gonna work for you, just do it. And if you start with something on here, you just like maybe, oh, that's too much, we need to like decrease the load. Whatever you would like. I mean, like I want to prepare you to the market in this field. If you understand and grasp all the information that I'm giving you in this class, I'm giving you like a really good experience that the market needs in this field. And I told you before, this market has much more money than other markets like the structural design or all the natural hazard here in the US, and I believe in the whole world. They like invest a lot in this, and they need a lot of people with expertise in these. So if you invest in your knowledge and what we are doing, you are gonna get a really good place after you graduate. Okay? All right. Just good luck with the exam next Tuesday. Bye.
Would you be providing